All right. Shall we? All right. Um, so I put in grades for test number 2 last night. I have them with me. So if you want your test back, just come by after class. I'll get it for you. Any questions about? Okay. So I mean, that was the last midterm before the final. So aside from homework grades, that's about, it's pretty good picture of kind of what you're going to be taking to the final. If you have any concerns or questions about where you stand right now, please email me. We'll talk about it. We can go over the tests in whatever detail you want. We can go over kind of what I think your prospects are. In my experience, most, if not almost all students underestimate where they are. So please talk to me if you have any concerns, and I'll give you my assessment of where things are. But yeah, if you have specific questions, please let me know. So let's get into chapter 6. We're going to talk about this idea called orthogonality, which is maybe not a word you've used a lot before in math, but it's probably an idea you have talked a bit about. So if I give you a vector 2, -5, could we find a vector that's perpendicular to that? What does it mean for two vectors to, or what does the word perpendicular mean? Let's unpack that. The inverse. So I'm going to treat this vector as, so let's say this is the vector 2, -5. Actually, it can't be. Negatives are important. So if this vector is 2, -5, does that tell me about like this? Let's think about this in terms of a slope. What's the slope of this straight line that I just drew? -5/2. So I went down 5. I'm going right 2. If we think about this in terms of a slope, do you remember how to tell if two slopes are perpendicular? How are they related to each other? Opposite inverse. What do you mean by that? Two-fifths.
I guess, yeah.
Okay.
The inverse of the slope times.
The inverse of the slopes. Okay. So one thing, maybe you've seen this in the past. If you have two slopes that are perpendicular, then when you multiply them together, that has to equal -1. Or another way to think about that is this: m1 is equal to -1/m2. So if you have a slope, the way to get the perpendicular slope is to take its reciprocal and flip its sign. So I'm guessing it's probably been a while for a lot of you, but I'm guessing you've all seen this idea of identifying when two slopes are perpendicular to each other. But now let's do this. Now that we have these slopes, so this vector that I first drew is 2, -5. What's this other vector? Let's call it v2. What would his components be? 5, 2, right? So it's going to go, for every 5 units I go to the right, I go upward 2. So by drawing this picture, we've convinced ourselves, hopefully, that these two vectors, v1 and v2, are perpendicular. Writing them as vectors, is this jogging memories you have about how to tell if two vectors are perpendicular? Do you remember something called the dot product or the inner product? So basically, this is a special kind of product we can take with vectors. It's a way of multiplying vectors together that always yields a single number, always yields a scalar. But the way we dot two vectors together So if I want to dot 2, -5 and 5, 2, then basically it's a sum of all these smaller products. So multiply the corresponding pairs of entries, 2 times 5 plus -5 times 2, 10 minus 10. So two vectors are orthogonal or perpendicular if and only if that dot product is equal to 0. So those two things are equivalent. And the reason I'm going to reuse the word orthogonal perpendicular is kind of by definition a two-dimensional spatial relationship. Orthogonality is much more abstract. It can happen in any number of dimensions. None of those dimensions have to involve space. It's just a way the two vectors are related, and it's all about this dot product. So I would bet that probably all of you have seen this idea. It might be deep in the memory warehouse. How are we doing with this idea so far? Good.
When we're doing this multiplication, it's not back multiplication, right?
No, in fact, so let me answer that in this way. Is this a multiplication I can do? No. So this doesn't exist. This dot makes a world of difference. Yeah. So another thing is this, like, what if I transposed one of them? What if I did 2 -5 times 5, 2 like that? Does that exist? It does, right? So this is a 2 by 1. This is a 1 by 2, and it'll make a something 2 by 2, right? So even these products even like are different in the kinds of things they yield. A dot product will always, always, always give you a single number, a scalar. Or you can think about it if you want as a 1 by 1 matrix, but it's always just one entry. Anything else? Okay, so we're going to use this to do a bunch of things, but let's talk about it first. So I want to describe all the vectors that are orthogonal to this vector 1, 4, 8. So these vectors, these are going to be totally generic, so I will just call them V equals x1, x2, x3. And I want to try to generalize or give some kind of a description of all the vectors that are orthogonal to 1, 4, 8. So if some vector V is orthogonal to 1, 4, 8, then what can I do with that word? How can I unpack that word or apply it somehow here?
Those two together and set it equal to 0.
I can dot these together and set that equal to 0. Another thing about dot products is they are commutative. It doesn't matter which one comes first. One times x1 is the same as x1 times 1. So this dot product equals 0. So let's actually expand this dot product. What does this come out to be?
1x1
x1
plus 4x3
plus 4x2
plus 8x3.
plus 8x3 equals 0. So what I'd like to do now is I'd like to come up with a basis for all the vectors that make this equation true. Is that something we know how to do? So a couple ways we can do that. I can write this as a matrix. And then could I find the null space of this one row matrix? I grant it's something I've never asked you to do before, but it's something we can do. How do you find the null space of a matrix? Right. So how many parameters are we going to need here? 2. So we know we're going to try to find a vector, a generic one that looks like this: x1, x2, x3. What do these things equal? What's x1 equal? -4x2 minus 8x3. And you said we need 2 parameters, right? So it looks like x2 and x3 are just playing that role. So v is going to be equal to something times x2 plus something else times x3. What goes in this first vector here? Or the first row, sorry. So -4x2 minus 8x3. Then x2 equals, or what's the middle row look like? 1, then 0, and then 0, then 1. So in trying to find the vectors that are orthogonal to this single vector, what we found is this. We found, let's just say it's the basis for it is these 2 vectors, -4, 1, 0, -8, 0, 1. So any vector that is built out of the combinations of those 2 things better be orthogonal to 1, 4, 8. Are we okay with that? Does it look like are the 2 vectors in that basis just alone, are they orthogonal to 1, 4, 8? Yeah, if you do the dot product, you should get 0 for each one. Which means if I enlarge one of them, you're still going to get a 0. If I add those together, you're adding zeros together. Anything you build based on those 2 vectors is going to be orthogonal to 1, 4, 8. Any questions on how we built this? Okay. So what we just found is something called the orthogonal complement. So if you have a basis for some subspace, then the orthogonal complement is basically it's the basis for all the vectors that are orthogonal to it. So basically what we just found is the orthogonal complement to a single vector, a subspace whose span is based on a single vector 1, 4, 8. All right, so let's go a little deeper. Let's build the basis for the orthogonal complement of this span. So this span has a basis of 2 different vectors. So let's think about the way we just handled the case of a single vector and scale it up here. What changes would we have to make, or what could we do that was identical to what we did before? So if I'm looking for the orthogonal complement of W, what are the vectors in that span going to look like, or what's going to be true about them? So one of them, both of them, has to be both, right? So basically, here's one thing we do know is that 5, 15, 3, 10, if I dot that with, I'll just call it a generic V again, that equals 0. Same thing is true for the other vector. So I'm starting from the same place. I know that if I do this inner product with any of the vectors in my basis, then I will wind up with that inner product of 0. So what can I do with these two pieces of information?
Do the dot product with x1.
Sounds good. So we get 5x1 plus 15x2 plus 3x3 plus 10x4 equals 0. Also 3x1 plus 9x2 plus 2x3 plus 5x4 equals 0. What did we do? So once we wrote down our equation last time, what did we do with it? I don't know if we can parameterize it in one shot this time. Because if I give you a 1-row matrix, usually when we find the null space of a matrix, what do we have to do with it to get the null space? But if I give you 1 row, we're already there. So I think that was having the 1 vector last time basically freed us from doing that. I think we need to reduce this one though. So let's write it as a matrix. 5, 15, 3, 10, 3, 9, 2, 5. I'm hearing calculators. So if we reduce,
Yeah, 1305.
1305, 001, -5. Okay. So if that's how this matrix reduces, what can we learn from it?
X1 equals negative 3x2 minus 5x5.
X1 equals negative 3x2 minus 5x5, 5x5. 4. I don't know if you said 5 or I heard 5. Either way, I believed 5. But it can't be. All right. What else?
X3 equals 5.
X3 equals 5x4. So how many parameters do we need? 2. Oh, wait, 2, 3. I think I'm just seeing 2. So the pivots are going to give you your lead variables. We got 2 of those, which means all the other ones are free. And there are 4 total variables. So you can also look at what variables exist on the right-hand side of these equations. It's x2 and x4. So now we can generalize x3 or x1 through x4, knowing that our parameters are being played by x2 and x4. All right. So we can drop in our x2 and x4. We know what those look like because those are parameters. What is x1? What's the x1 row going to look like? Negative 3x2 plus negative 5x4. And then x3 is 0x2 and 5x4s. So the basis we found has what dimension? 2. So negative 3, 1, 0, 0. Negative 5, 0, 5, 1. Questions? All right. So now we've find some orthogonal complements. Now we're gonna like work this idea of a orthogonal basis. So something we have not required of any of the bases we've dealt with before, but as we're gonna kind of build up to. So first, let's verify this. Are these three vectors orthogonal? How could we answer that question? So we've talked about what it means for two vectors to be orthogonal to each other. How do we do that for a set of more than two vectors?
You just dot them all together.
At the same time? So let's think about that. What happens if I dot all these together? So 1, 2, -2, 0, dot 2, 4, 5, -6, dot 2, -5, -4, -6. Is this, can we do this? If I dot these two together, what do I get? You get a number. And I can't dot scalars with their vectors. So a dot product is a thing that only works for two vectors. So because of that, if we're going to try to determine if three vectors are orthogonal, we can only look at them in pairs. So basically what we have to do is look at all the different pairs here. So how many different dot products do I need to take? 3. So I already wrote down one of them, so let's make sure. What's the dot product here? Is it 0? 2 plus 8 minus 10. Good. It's not enough, though. What else do I need to do? Okay. Which one do you want to do next? First and third. So -1, 2, 2, 0. Dot. 2, -5, -4, -6. How's that one work? Plus 8. Plus 0. Great. And finally? Second and third. 2, 4, 5, -6, and 2, -5, -4, -6. We got 4 minus 20 minus 20 plus 36. Is that 0? Yeah. Okay. So the dot product is this purely binary thing. You can only do it with two vectors. So one word that I'll throw in here to kind of hammer home how to do this. If you're saying that a set of vectors is orthogonal, you're really saying is that they are pairwise orthogonal. Because you can't investigate all three vectors at the same time. So basically you have to look at all the different pairs that exist. So for this case, that's 3 different pairs. Questions? Okay. So now that, did I skip a thing? No, I didn't. So these are the 3 vectors we just dealt with. I'm asking you to take it on faith that they're a basis. We could prove it, but they are a basis for some subspace. Can we find the coordinates of U with respect to B? Something I asked you to do something a lot like this yesterday. What's that? Ooh. We could do that. Well, let's think about it. So we know that if we take the basis B and multiply it by some mystery thing V, I'll get U, right? So essentially I want to solve for V. How would I solve for V? Inverse B on the left. So this is what you would have to do, right? So in general, this will work, right? But now I'm telling you this is an orthogonal basis. So there's something we can do that, actually, what's the order I want to do this in? Yeah, that's the order I want to do this in. This will work, but now that we've verified that this is a basis, that all the vectors are pairwise orthogonal, here's something else we can do. We can dot these things together. So the vector U is the one I'm interested in. And now here's what we know about. I'm trying to think of the right way to say this. Here's a benefit we can draw on the fact that these were orthogonal. So I know that C1 times this, 1, 2, negative 2, 0, plus C2 times 2, 4, 5, negative 6, plus C3 times 2, negative 5, negative 4, negative 6. That will equal this. Negative 3, 12, 6, 12. So when I'm trying to figure out what these C1, C2, and C3 are, with any old basis, with any generic basis, let's say I figure out that C1 is like, I'm going to do 3 of C1 because I know that, or negative 3 of C1 because that'll get me to that negative 3 in the first component, right? But then that's going to get messed up if I add the other vectors together, because that is going to mess up that component that I have in the first entry. If your vectors were orthogonal, then basically what you're doing is this. So I'm trying to, this is going to be just symbolic, but if I'm trying to get from here to here, and the only vectors I'm allowed to use are orthogonal or are perpendicular to each other, then what I'm really looking at is I'm adding two vectors together that don't really have anything to do with each other, because the direction of one vector is totally perpendicular, totally orthogonal to the vector of any of the others that I'm allowed to use. So in a way, it really simplifies what I'm trying to find. So let's do this. I'm going to find, let's call these things V1, V2, and V3. Let's find these dot products of U dot V1, U dot V2, and U dot V3. What is U dot V1? Negative 3 plus 24 minus 12. Double check me. 9. And next, negative 6 plus 48 plus 30 minus 72. So what did we just learn about U and V2? Unless you disagree with me, but I think that dot product is 0, right? So what did we just learn about U and V2?
They're orthogonal.
They're orthogonal. What does that tell us about the value of C2? Any idea yet? Maybe let's hold off on that. So what about U dot V3? -6, -60, -24, -72. Okay, someone double check me. I think that's okay. Yeah. So let's talk about this. Like, what did we just find? When we dot two vectors together, what's the purpose? What does that product tell us? Because we've talked about what it tells you when the answer is 0, we know exactly what that means, right? When the dot product is 0, what does that mean about the two vectors that I dotted together? Perpendicular. What if the dot product is very close to 0? What should that mean? It's not quite 0, but it's very close. Not perpendicular, but what could we say about that angle? Maybe it's not. It's what? It could be acute, but what if it's like -0.001 or something? It'll be obtuse, but it'll be close to what? 90. So that's something we can generalize about the dot product. It's really the purpose of it is to give you a sense of what the angles between these two vectors are like. When it's 0, you can say right away, oh, that's 90 degrees. They're perpendicular, they're orthogonal. When it's any other number, we don't really have a good idea. But we can get a better idea if we, because like I don't know if 9 is a big number in relation to this, because I haven't looked at how big the actual vectors are. So that's something we could do. How could I find the magnitude of vector B1? What if vector V1 was only those two entries? How can we find the length of it? Not 1 times 2. So let's go back to one of the very first things we did with the vector was, let's say I have the vector 1, 2. I could write that as, if it goes to the right 1 and up 2. So this is the vector 1, 2. And I want to find exactly how long that is. So from the beginning to the end, how could I find that magnitude?
Square root of 1 going squared plus the other.
Right. So it's Pythagorean theorem. So 1 squared plus 2 squared equals whatever the length is. So in this case, that'd be radical 5. Squaring is just the same as multiplying by itself, right? So 1 times 1 plus 2 plus 2, or sorry, 1 times 1 plus 2 times 2. That's the same as what we just did, right? Because of that, we can use the dot product to kind of figure out how long a vector is. So let's do this now. V1 dot V1, V2 dot V2, and V3 dot V3. What is V1 dot V1? Nine. V2 dot V2. 4 plus 16 plus 25 plus 36 81. And then the last one, 4 plus 25, plus, this is the same thing, plus 16 plus 36, also 81. So basically when I dot a vector with itself, basically what I'm doing is I'm squaring all the components and adding them all up, right? That's almost the same thing as the Pythagorean theorem, except I'm not doing the square root at the end. Basically, when you dot a vector with itself, you're going to get the square of the magnitude. So why did I have us do these 3 pairs of dot products? So since these vectors are orthogonal, I know that the direction of v1, v2, and v3 have nothing to do with each other. So I can look at basically the relationship of these dot products, and this can kind of tell me everything I need to know about what C1, C2, and C3 are. U dot V1 is equal to 9. V1 dot V1 is equal to 9. So that suggests to me that C1 is going to be equal to 9 over 9, which is 1. So this is something I'm allowed to do because I know that vector 1, vector 2, and vector 3, their directions are all completely independent from each other. C2 is a little bit trivial, but I'll write it down just in case. That'll be equal to U dot V2 over V2 dot V2, which is 0. And then C3 will be equal to negative 162 over positive 81, which is negative 2. So if what I told you is true, then I should be able to drop these things in. 1 of these plus 0 of these minus 2 of these should give you the vector that I wanted to find. Do we believe it does? It looks like it does. So I really need to caution you, this only works for certain kinds of bases. So what's special about this basis that we've never actually looked for before? What was true about the 3 vectors in this basis? They're orthogonal. So this dot product, this approach only works if the basis is set up that way. So there's a lot of value in having a basis that we know is made up of orthogonal vectors. And this is only one of the reasons we might want that. Any questions about how we found the things we found? All right. So now let's do this. I want to know, is U in the span of B? So this is something we've done several times. How could we find the answer to this? Okay, so what would the augmented matrix look like that I'd want to build?
It'd be all those p values on one side.
Okay. So basically, I'm trying to solve this equation. So right now, this has nothing to do with the fact that the basis is orthogonal. This is something we can just do. If we reduce this, what do we learn? Okay, so you get the identity basically. What does that mean for us? Nope. It's not in the span, right? So we essentially found that 0 = 1. So this failed. So we know that U is not in the span of B, but what we can do, we can still do this dot product approach because we have an orthogonal basis. And what that'll give us is the vector that's in the span of B that comes closest to U. So let's do this. We know that V1 dot V1 is equal to what, 9? V2 dot V2 is equal to 81. And then V3 dot V3 is equal to, they're both 81? Okay. All right. So we can rely on that from the prior example. But now let's do this. We know that U is not in the span of V, but we can still take this dot product. What is U dot V1? -2 plus 6 minus 4 plus 0. Is that right? Or did I just want that to happen? Yeah. And then U dot V2 -4 plus 12 plus 10 minus 24 minus 6. And then U dot V3 -4 minus 15 minus 8 minus 24. Can we agree on all these dot products? So if we take the same approach as last time, we can still find C1, C2, and C3. So C1 should be equal to 0, 0 over 9. Basically, we found out that U and V1 are totally perpendicular. What about C2? I get -6 over 81, which I'm going to reduce it. -2/27. And then C3 is equal to -51 over 81, which is -17 over 27. So reducing the matrix told us that this vector U is not in the span of D. But what did we just find with these constants C1, C2, and C3? So let's find out. What is -6 over, I reduced it for a reason, -2 over 27 times this vector 2, 2, 4, 5, -6, minus 17 over 27 times 2, -5, -4, -6. So if we add those together, what do we get? I'm going to let you correct me for all the fractions I'm doing. I think those are okay. Whenever somebody has them, give me the decimal approximations for all these fractions.
Negative 1.1.
Okay.
2.85.
2.85.
2.15.
2.15. 4.22. Okay, so that's a vector. Is that vector in the span of B? The one that we just wrote down? Has to be. That's how we built it, right? We took a combination of V2 and V3. If you compare that to vector U, what do you notice? It's not far away from that. None of those component values are very far away, right? So even though U is not in the span of B, what this process allows us to do is we found the vector that is in the span of B that comes closest to U. So kind of metaphorically speaking, what's going on here is let's say this vector right here, this represents all the vectors in B. And right here is vector U. There's some difference between them, and that has to be perpendicular. So there's some vector K that I could add to something in B, which I'll just point to this. The vector in B that I actually drew is this one because that's the closest one. So I could find that vector K that basically bridges the gap between those two vectors, but this process does allow me to find the closest one. Questions? All right. So basically generalizing what we just did, this is basically how we found those coordinates. But this only works in this case if we have an orthogonal basis. We can use this ratio of the dot products here. So what did we do for all the different like vectors in the basis? We did two different dot products. One of u dot v and the other one with v dotted with itself. And we multiplied that ratio by whatever the vector is. So basically this right here gives you a c value, and then c times v basically tells you what combination of that vector do I need to get the vector in my span that I actually care about. So this is called an orthogonal projection. So another way to look at the orthogonal projection, let's say this. Let's call this vector v. Let's call this vector u. These are not orthogonal, right? Even though they're not orthogonal, something I can do is this. I can break up u into two different pieces. A part that is parallel to v and a part that is perpendicular to v. And basically, for the example we just did, what we just found was the part of u that was parallel to things that are in v. I found the part of u that could be in the span. So something I know we've all done a lot of is, let's say this vector is what, 3, 4? 4, 3? It's convenient to think about this being the sum of two vectors that are perpendicular to each other. One that's purely horizontal and one that's purely vertical. So this is a very special orthogonal projection where the two orthogonal directions we're looking at are horizontal and vertical. You can always do that. It's not always, you don't have to limit yourself to horizontal and vertical, you can basically break apart those directions any way you want into two perpendicular directions. So that's essentially what we just did. We're letting vector v dictate one of those two directions. How are we feeling? All right. So let's do one more. Is this thing in the span of B? Do we need the augmented matrix to tell us this? Or could we jump straight to our dot product scheme? Will that dot product method even work here? How can I check if the dot product approach will actually work? If B is orthogonal. So is B orthogonal? Right. There's only one pair of vectors in it, so I just have to do one dot product. Two plus 8 minus 10. That's good. So can I do my dot product approach? Right. Tell me how to set that up. So, okay, so let's name these V1 and V2. So what is V1 dot V1? I don't think it's 7. It'd be 9. 9. Should also do V2 dot V2. $45. All right, so we definitely need those. What else do we need? Do U dotted with the same vectors. U dot V1 is equal to 3 plus 22 plus 38, 63. And then U dot V2. 6 plus 44 minus 95. All right, so I got all 4 dot products that we would need. So what should I do with them? So what is C1 going to be? 63 over 9. 7. And then minus 45 over positive 45 is negative 1. So here's what I found. I found that, what do I know about this vector that I'm writing down? 7 times 1, 2, negative 2, plus 1 times, no, minus 1 times 2, 4, 5. After I add these things together, what would that give me?
311.
311 what?
Thanks for negative.
311 negative 19. So can I answer my question now? Wait, is it 3? 7 minus 2?
I'm just reading the view.
Oh, yeah. So we're not guaranteed to get U back. So this will be 5, 10, negative 19. So yeah, the one thing to keep note of is that we're not guaranteed to get the vector U back when we do this. What are we guaranteed to get back? Something what? Orthogonal to B? Not orthogonal to B.
It's in the.
Something that's in the span of B. We can say, so that is true. We can even be a little stronger than that. So 5, 10, negative 19 is in the span of B. What's also special about this vector in relation to U? It's the closest thing in the span of B to U. So can I say U is in the span of B? It's not. Because if it was, I would have gotten U. Instead, I got this other thing that is relatively close to it. It's off by 2 units in one direction, 1 unit in another. The third components match, but otherwise they're not the same. So no, U is not in the span of B, but this is as close as I can come to it. How are you feeling? All right. So got a few minutes left to start. Next thing. So yeah, going forward, especially in this chapter, we're going to talk about, orthogonal bases have a lot of things that you get for a lot of benefits you can use if your bases are orthogonal. So let's talk about how to construct them. So I have 2 vectors, 3, 1, and 2, 2. I would like to make a basis for the same span that's orthogonal or whose basis is actually orthogonal. So is S an orthogonal set right now? No. So if I dot this 3, 1 and 2, 2, I get 6 plus 2, which is 8, which is not 0. So I would like to replace this with something that is orthogonal. So let's kind of draw a picture of what these 2 vectors look like. What does 3, 1 look like? That's going to be something like that. And my other vector is 2, 2, which is basically a 45-degree angle. So we're not orthogonal. So what I would like to do is replace, this picture with something that looks like this. So again, we're going to try to make orthogonal vectors. I don't need one to be totally horizontal. I don't need one to be totally vertical. But I would like them to be orthogonal. Because of that, what I'm going to do is this. To try to build a new basis, we're going to build it up vector by vector. So that first vector, I'm just going to take it as is. I'm going to take 3, 1. So V1 is equal to 3, 1. V2 is equal to 2, 2. This is my old basis. In my new basis, I'm just going to keep 3, 1. U2 is going to have to be different, though, because I want them to be orthogonal. So I can start wherever I want, though. So basically what I want is this. I have this vector 3, 1. And I have a vector 2, 2. Which is not orthogonal to it. But something we talked about in the last section is this. I can break up a vector into 2 components. One that is perpendicular to a direction I care about, and one which is parallel to a direction I care about. So here's the game. 2, 2 has these two components. I don't want this one. I want this one. I want the one that's going to be orthogonal to tree 1. So if I can identify what those two pieces are, then I get the thing I want. So how can I identify what these two pieces are? So even though I don't want it, even though it's not the desired end result, I'm going to find the parallel part of this first. So that is the orthogonal projection. I want to find the orthogonal projection of 2, 2. So of V2 onto U1. Do we remember how to find that? I mean, we literally just did it, but I grant you this is a totally different context. So we should go back to the last set slides. Basically, what we're looking for is this. I want to find this thing here, this U dot V over V dot V. Basically, that right there is going to give me a scalar multiple of the vector that I care about. So I want U dot V over V dot V. So what are those dot products going to be? So I don't need to do V1. So this process that we're kind of building up on, basically I'm trying to get, so from S, which is just a generic basis with no orthogonal like characteristic to it, I'm trying to turn that into a basis that does two things. It spans the exact same subspace, but its vectors are orthogonal. So for simplicity's sake, I'm just going to say that, all right, my new vector 1 is identical to the old vector 1. But I can't keep the old vector 2 because it's not orthogonal to vector 1. So that's why I'm trying to like basically decompose 2, 2 into these other pieces. So you suggested doing U.V1, sorry, U1.V1 and U1.V2. I don't really need to do U1.V1 because I just took that vector as is. So because of that, let's rewrite what I'm doing here. I'm going to do U1.V2 and divide that by V2.V2. So U1 in this case is the same as V1. V2, 2, 2 over 2, 2 dot 2, 2. What does that come out to be? Oh, sorry, what was it? 8 over 8? Oh, that's so convenient. Like I planned that. So this comes out to be 1, right? So 1 times what? Actually, I think I lied to you all. I did lie to you all. I'm very sorry. Because what's the direction I want to find here? Do I want to find something in the direction of V2 or in the direction of U1? Did you say V1? That's not one of the options I gave. So I want to find in the direction of U1. And again, it's just a means to an end. The thing I really want in the end of this is to find where the check mark is. I want to find that, but that's really hard to do directly. So I know that 2, 2 is the thing I'm breaking down. I know how to find the part of that that's parallel to U1. But to do that, I have to do the right dot product, which is not what I just asked you to do. What is U1 dot U1? 3, 1, 3, 1. So that becomes 8 over 10. Okay. So basically, what have I learned here? I've learned that if I take 8/10 of U1, that will give me the parallel piece. So what is 8/10 of U1? Should be 2.4, 0.8. I just multiplied 3 and 1 by both by 0.8. So now what I'm going to do is this. I'm going to draw a new picture. And I have this vector 2, 2. And now I can draw this as a perfect right triangle because I know the exact length. I just found it. 2.4, 0.8. And now how can I find this thing here that I'll call K? What's that?
Would be equal to this.
No, so here's what I'm trying to get a handle on is like how long ago this stuff is in your past, or maybe it's not there at all. But does the phrase with vector addition does tail to tip sound familiar to anybody? Sort of. That's one way we can think about adding vectors together. So this vector along this like hypotenuse here, that's 2, 2, right? If I add any two vectors that start from the same place and end at the same place, then that sum has to be the same. So that's what I'm going to rely on here. I don't know what K is equal to, so I'm just going to call it A and B. But the fact that I can add vectors that way means I know I can do this. 2.4, 0.8 plus AB equals 2, 2. What does that tell me about what A and B are? Negative 0.4, and B is 1.2. Okay, so now that we have values, let's take stock of like what I said the whole point was. We wanted to replace this basis with a new basis whose vectors were orthogonal. Let's make sure we actually did that. So we said that U1 was equal to 3, 1. And we just found this thing, which I'm going to call U2. Are these things perpendicular? When I say these things, I mean U1 and U2. Is U1 dot U2 equal to 0? Three times negative 0.4 is negative 1.2. 1.2 times 1 is positive 1.2. So here's what we've done. We have replaced S with this new basis. 3, 1. So it shares something in common with the old basis. And I'm not going to adjust the lengths. Negative 0.4, 1.2. So it's going to span all the same vectors, which is something that we'll talk about next time. But hopefully we can see for sure that it accomplishes the other goal of being orthogonal. So this is a process we'll get into more next time about basically we can, given any basis, we can transform it into an orthogonal basis from scratch. So I got 2 10, so let's do that next time.